Okay, today we are going to study where's my scratch paper? Okay, so previously we studied TDS relation. What was the TDS relation? TDS relation means TDS is going to be du plus TdV. That's what we derived last week. If you don't remember, we can go from the beginning. So the energy balance equation in a differential form is going to be del Q minus del W is going to be du. So the rate of the net heat transfer minus the net energy transfer by work is going to be the change in its internal energy, which is du. From this, according to the definition of entropy ds is going to be del Q over T when it is internally reversible. And energy transfer by work can be determined by pressure times the change in volume. So if we say this equation is internally reversible, then we can replace the first term with TDS, and the second term with TdV. So TDS minus PdV is going to be du. If you move this one to the right-hand side, you get this equation. That's what we did last week. Okay? Then let's look at this equation. Now, using this TDS relation, we want to determine how this entropy change. How do you determine, the entropy change? It's simple. Entropy at the final state S2 minus the entropy at the initial state S1. So we want to determine S2 minus S1. How can we do that? You can integrate ds. So let's integrate ds. How can we? We have a temperature in front, so we want to get rid of this temperature. So if you want to get rid of this temperature, you can divide each term by temperature T. So divide by T, divide by T, divide by T. Then what we get? ds is going to be du over T plus TdV over T. Now, if you integrate this ds from the initial state number 1 to its final state number 2, you get S2 minus S1. Okay, sounds simple, so let's do that. So I'm going to integrate this one from 1 to 2. Integrate this one from 1 to 2. Integrate this one from 1 to 2. So, can you integrate ds? Yes. The solution is going to be simple. S2 minus S1. What about this? Can you integrate du over T? No, we can't, unless you know the relation between T and U. So, to integrate this one, we need to know the relation between T and U. Is there any equation that has U and T together? Yeah, there is one equation that has u and t together. u2 minus u1 is cvt2 minus t1, so you have a u and t together. So I'm going to use this equation. u2 minus u1 is cvt2 minus t1. But this one is du, not just u. So let's find du. How can we do that? We need to find the differential form of this equation. Then what is it? Difference in u is Cv times difference in temperature. Then you can replace this du with Cv dt. So the Cv dt is going to replace du. What about the last term on the right-hand side? Pdv over t. Can you integrate it? No, we can't, unless you know the relation between among t, and v. So, is there any equation that has t, v, and t? Yes, the ideal gas equation. Tv is RT. Then, what is the form here? It's going to be P over T. So, I want to find P over T. How can you do that? If you divide each side by T, you will get P over T. So let's do that. So I'm going to divide each side by T. But there's one problem. We have a V. So I want to get rid of this V. By how? Dividing by V. So I'm going to divide this by TV, not the television, temperature, and specific volume. Then what do you get? We get P over T is R over V. So I'm going to replace this P over T with R over V. Then we are going to have integral from 1 to 2 dv dt over t plus integral from 1 to 2 r over v, r dv over v. Now, can you solve it? Not yet, because we don't know the relation between Cv and T. Then there's one way to solve this one. We are going to assume assumption. We are going to assume Cv excuse me, is constant. If Cv is constant, this one can come out. Constant can go anywhere. What about this R? Is it constant or a variable? What is the name of this R? Gas constant. So this is a constant. It can come out. Cv can come out. So because Cv is constant, this one comes out of this integration. This R goes out of this integration. So what do we have? Integral of dt over t. Integral of dv over v. So how can you solve it? Integral of dx over x from 1 to 2 is going to be natural log x2 over x1. Then what is dt over t? Dx over x is going to be natural log x2 over x1. dt over t is going to be natural log t2 over t1. So this term is going to be Cv natural log t2 over t1 plus, now r goes out, r times natural log v2 over v1. So This is how you determine the change in specific entropy S2 minus S1 when you have a gas system. Gas. Any question? Not really. It's not that difficult, right? Then, is that it? Not yet. Let's do it one more time. So there's one equation. I need a scratch paper. Let me write the back of this one. Okay, so we got one equation. Now the second one is going to be, let's start with this TDS relation. TDS is du plus PdV. Then we have P times V here. So let's talk about P times V. P times V. What is the differential form of this P times V? What is D of P times V? Do you know how to solve that? It's going to be PdV plus VdP. Then we have a PdV here. Then there is a PdV here. So why don't we move this one to the other side? We can do that. D of PV minus VdP is going to be PdV. Wait. Now we have a PdV. PdV. Can we replace this one with this? Yeah, we can do that. Then this TDS relation becomes TDS is going to be du plus d of PV minus VdP. Wait, we have a u inside d, we have a PV inside d, so let's combine them. Then this one becomes TDS is d of what? U plus PV minus VdP. Then, don't you think that this one looks familiar? U plus PV. Have you seen it? U plus PV. What is the definition of enthalpy H? U plus PV from chapter 3, right? So we have a U plus PV. Can we replace this U plus PV with H? We can do that, no problem. So we can replace this U plus PV with H. Then we have TDS is DH minus VdP. Now we can do the same. Divide by temperature T. And integrate from 1 to 2. From 1 to 2. From 1 to 2. Then the first one, we can cross T out. The left-hand side becomes S2 minus S1. Now we have dH over T. Can you integrate it? No, you can't, because we do not know the relation between H and T. So we need to find an equation has H and T together. That is this one. H2 minus H1 is CpT2 minus T1. But this is not in a differential form. So what is the differential form of this equation? dH is Cp dt. dH is Cp dt. Oh wait, we have a dH. We have a dH. So can we replace this dH with this one? Yes, we can. What about the last term? We have a Vt over T. Do we have an equation that has V, T, and T all together? Yes, the ideal gas equation. TV is RT. But what is the form? V over T. Can we have a V over T? Yes, we can divide by temperature T. Then what about this P? Oh, we can divide by pressure P. Then what do we get? Tp Pt. So the equation is going to be V over T is R over P. Then you see V over T, V over T. So can we replace this V over T with R over P? We can. Then this equation becomes integral Cp dt over T minus integral R dP over P. Now, if we assume Cp is constant. If we say Cp is constant, then this Cp goes out. This R is a constant, goes out. Now, do you know how to integrate dt over T? Yes, natural log. So this equation becomes S2 minus S1 is going to be Cp natural log T2 over T1, because integral of dx over x is going to be natural log x2 over x1. So we do the same, minus R natural log P2 over P1. So there's another equation. So we have two equations, this one and that one. But there's one limitation, which is that this equation and the equation on top, they are only valid when specific heats are constant. Then what about specific heats are not constant? Assumption. Cp is not constant. Then can you integrate this one? Not anymore. You cannot integrate this one. If Cp is not constant, this Cp cannot go out. So you cannot solve this equation. So what can we do? We can use a table. In that case, we use a table. S2 minus S1 is going to be, since we cannot solve this one, I'm going to say S degree 2 minus S degree 1, that represents this one, minus R natural log P2 over P1. Then where can we find this S degree? From a table. So there are three equations, 1, 2, 3. That's how we evaluate the change in specific entropy. This one, this one, and this one. These three equations are shown Here. Over there. That one is this one. The second one is this one. The last one is this one. So here is the first two equations assuming constant specific heat. The last equation assuming variable specific heat. Okay? So what you need to do is that write down these three equations and use the first two when you can assume constant specific heat. Use the last one when you cannot assume constant specific heat. That's how you determine the change in entropy. Any question? Then is that it? No, we have one more. On this slide, we studied how to determine the change in entropy because our assumption is that entropy should change. Is that assumption valid? Yes, whenever there is an irreversibility, whenever there is an energy waste, entropy should increase. Then what about if you have a reversible process? Then entropy remains constant. Then let's talk about an ideal case when entropy remains constant. So we have these three equations. Now I'm going to assume entropy S remains constant. What kind of, the process is that? It is called isentropic process. That means entropy S remains constant. So the change in entropy is 0. In other words, S2 minus S1 is going to be 0. Then, is there any equation that we can use for an isentropic process? Yes, there is. We can find them from these three equations. So let's use the first equation. The first equation is this one. When we assume entropy remains constant, the left-hand side of this equation goes to 0. So 0 is Tv natural log T2 over T1 plus R natural log V2 over V1. The left-hand side seems to be empty, so let's move one to the other side. I'm going to say minus Tv natural log T2 over T1 is going to be R natural log V2 over V1. In this equation, do you want to use this equation as is? For me, no. Why is that? Because I don't like one thing. This one is this natural log. Can we get rid of them? Yes, we can. But how? Let's see. I want to, clear in front of this natural log. So we have a minus Cv. So can you get rid of this minus Cv? Yes. Divide by minus Cv. Divide by minus Cv. Then what we get? We get natural log T2 over T1 is going to be R over minus CV natural log V2 over V1. Then there's one thing that bothers you. What is that? R over minus CV. So, can we get rid of them? Yes, there is a one way. R is Cp minus Cv. That is called specific heat relation. And there's one more. The specific heat ratio, Cp over Cv, is called K, no, kappa. This is not K, this is kappa, the Greek letter. Kappa. Anybody from Greece? No one here, right? So if I say kappa, you gotta believe me, right? So, and there's one more thing. I don't like this negative sign. Then can we get rid of it? Yes. By how? Minus natural log x2 over x1 is what? Natural log x1 over x2, right? If you don't remember, yeah, now you can remember. So, R is going to be Cp minus Cv. So let me say natural log T2 over T1 is going to be Cp minus Cv. And we have a negative sign. I'm going to get rid of it by switching these two. Natural log V1 over V2. And there is a Cv. Okay, Cv. And this one can be rewritten as Cp over Cv minus 1. Natural log T2 over T1 is going to be Cp over Cv minus 1 natural log V1 over V2. Now, there's a kappa. Is going to replace this one. And A natural log B is going to be natural log B to the power A. You know that, right? The same thing. There's a kappa minus 1 goes on top of this. Natural log T2 over T1 is going to be natural log V1 over V2 to the power kappa minus 1. Now, we have nothing in front of this natural log, nothing in front of this natural log. You can get rid of them. Then, what is the governing equation? T2 over T1 is going to be V1 over V2 to the power kappa minus 1. This is temperature volume relation when we have an isentropic process. Any question? Finding this relation? No? Okay. So we got that equation from the first S2 minus S1. So we got this equation. Then why don't we look at the second equation? Can we do that? Yeah. If we say isentropic process, S2 minus S1 is going to be 0. So can we move this one to the other side? Yes. So for this one, S2 minus S1 is 0. With that assumption, the equation is going to be Cp natural log T2 over T1 is going to be R natural log T2 over P1. Done. Okay. Wake up. Then you want to get rid of this CP and R. How can we do that? We can divide each side by CP. CP. And this R is CP minus CV. Then this equation becomes natural log T2 over T1 is going to be 1 minus CV over CP. Natural log P2 over P1. Then, according to this one, CV over CP is going to be 1 over kappa. So this equation becomes natural log T2 over T1 is going to be 1 minus 1 over kappa. Natural log P2 over P1. Or some people like to say kappa minus 1 over kappa. Natural log T2 over P1. They are the same thing. Now, this one can go on top of this pressure because of this relation. This becomes natural log P2 over P1 to the power kappa minus 1 over kappa. Now, can you get rid of this natural log? Yes. Then what is the relation? P2 over P1 is going to be P2 over P1 to the power kappa minus 1 over kappa. That is the relation between temperature and pressure. Then we can do one more. T2 over T1. T2 over T1. So the right-hand side of this equation should be the same as the right-hand side of this equation. This one and this one. Whew. P2 over P1 to the power kappa minus 1 over kappa is going to be V1 over V2 to the power kappa minus 1. Then you can multiply by, we have a kappa minus 1 here, kappa minus 1 here, so you can get rid of them and multiply by kappa. Multiply by kappa. Then what do you get? P2 over P1 is V1 over V2 to the power kappa. So, I'm sorry. 1, 2, 3. Temperature, pressure, volume relations for an isentropic process. That's everything about the theory part of entropy in this chapter. Any question? You may not be, very familiar with these equations. So there's one way we can do solving a problem. So let's solve a problem together. By the way, this is isentropic process. And we have a heat equation here and here. So let's solve this problem. We have an insulated piston cylinder device. Initially contains 300 liters of air. And at 120 degrees Celsius, I don't have a, I'm doing this one. And we have a resistance heater placed inside the cylinder, and it's going to provide energy transfer into this air. And we are going to assume that air pressure maintained constant. So we have a constant pressure process. And we are going to calculate entropy change. So let's do that. If you want to calculate the change in entropy, you need to know the temperatures between the initial state and the final state. We know the initial temperature, which is 17 degrees Celsius. That's good. And do you know the final temperature? Unfortunately, we do not know the final temperature. So before determining the entropy change, we need to determine the final temperature. How can we determine the final temperature? By using energy balance equation. So let's write down the energy balance equation. There are two energy balance equations that we studied, one from chapter 3 for a closed system, the other one in chapter 4 for an open system. So we need to determine whether it is a closed system or an open system. It's a piston cylinder device. The mass of air remains constant. Therefore, it is a closed system. Then what is the energy balance equation? The energy balance equation for a closed system is going to be Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. However, when you have a constant pressure process, the right-hand side is going to be mass times H2 minus H1. This is only okay when you have constant pressure process. Then it says that it is insulated, so we neglect heat transfer crossing its boundary, and there is a resistance heater. It's going to provide energy to the system, that is this W, and there's no W out. Then how can you determine mass times H2 minus H1? H2 minus H1 can be determined by specific heat, T2 minus T1 times mass. It's going to be W in. Then what is this W in? Oh, we have 200 watt. So can I say W in is 200 watt? We can't, because watt is the unit of power. This W is not power, it's work. And to get the power, we need to divide by time. Then how do you get the work from the power? Multiply by the time. So you need to multiply by the time t, delta t. What is the delta t? 15 minutes, which is 900 seconds. Then what about the mass of the system? Do we know the mass? Unfortunately, we do not know the mass. However, we know the volume, we know the pressure, we know the temperature. Then you can use the ideal gas equation of a state. PV is MRT. What is P? 120 kilopascal. What is V? 300 liters. And 1 cubic meter is 1,000 liters. So 300 liters is 0.3 cubic meters. What is the gas constant R of air? 0.287 kilojoule per kilogram Kelvin. temperature T, 17? No, 290 Kelvin. So we have everything but mass M. Can you determine mass M? Yes, you can. This one goes into this equation. Then what is the initial temperature? 17 degrees Celsius. So we want to determine T2. If you know CV, you get T2. Okay, so if we get CP, we get T2. What is CP? CP of air is available in this table, table A20. So which one? If you look at the table, we have so many values here. So which one we are going to use? Just randomly select one of them and then solve this equation? We can do that, but don't do that. Then what specific value we are going to use? We need to use the average temperature. The specific heat evaluated at its average temperature. So what is? We have only 1 minute. Okay, so we can use iteration method. So what is iteration method? So we cannot solve the energy change for now, but let's determine the final temperature. So we are going to use iteration method. Iteration method means we are going to assume I think the final temperature is going to be this number. And based on this number, find average temperature and use this average temperature to determine CP. Once you determine CP, solve this equation, and then you will get T2. Then you are going to compare this T2 and your assumption. If they are far away, go to second iteration. In this second iteration, your guess is going to be the value that you got from the first iteration. So this one goes to T2. Then find average temperature and determine CP and find T2. So that's what you're going to do. Okay? But it's always better to practice together. So on Thursday, we are going to assume the final temperature and then solve this and verify whether our assumption is okay. If it is not, we go to second iteration to determine the final temperature. That's what we are going to do this Thursday, okay? Any question? See you on Thursday. Thank you.